All right, this is it. This is the last section of chapter 11, and then we have an exam on Friday. So Wednesday we'll review and then take the test on Friday. So um, there's really nothing new here in this chapter. So you'll be glad that it's a fairly short, another fairly short section. But today we're going to talk about the fundamental theorem of calculus, which is the bridge between the derivative and the integral, and it sets a stage for the antiderivative, which we're going to cover in chapter 12. So let's take a look at what the fundamental theorem of calculus says. It just says that if f prime, so it's capital F prime of t, is a continuous function between a and b, then the integral of f prime, this derivative, is equal to the difference between the value of the function at b and the value of function at a. Okay? So in other words, the definite integral of a derivative of a function gives the total change in the function. Which, if you remember from the last lecture, which I have right here, let me see. Don't like the way this thing scrolls, but okay. We said that if f of t is the rate of change of a quantity, then the integral of that rate of change is the total change between a and b. So this is just the fundamental theorem of calculus is just another way of saying that exact same thing. So like I said, there's nothing really new here, but you can see that we're integrating a derivative and we get information about the original function, right? We get the change in the original function. Like I said back when we were covering 11.1, there are situations where we're given information about a rate of change of a quantity, and we want to go backwards. We want to sort of derive it. We want to do the antiderivative, right? We want to find information about the function itself, and from the behavior of the derivative of the function. So that's where we're going with all of this. Let's take a look at an example where we can apply the fundamental theorem of calculus. Now, we don't. My guess is you already know how to do this problem. If I did not give you the fundamental theorem of calculus, you would be able to do this based on what you've learned already. And because, like I said, there's nothing really new here. If you know that if you integrate a rate of change, you get the total change in a quantity between over an interval, then you can do this too. But we're gonna do this using the fundamental theorem of calculus. Okay, so a physics problem. I love physics problems. All right. A ball is tossed with an initial upward velocity of 20 meters per second from the roof of a 60-meter tall building. And we have a graph of the ball's velocity. And we're asked to fill in this table of, and the table is of the position over time. Okay, so the velocity is the derivative of the displacement. Okay, and so basically we're given information about the derivative, and we want to get information about the function itself, right? Okay, so now we know from the fundamental theorem of calculus that let's just focus in on figuring out what's the distance, or displacement, I guess in this case. What's the displacement of this ball at t equals 1? Or I guess I should say this should say t. I guess I didn't realize I got a mistake here. This should say t. I don't know. I got t everywhere else. Okay, so at t equals 0, we're starting at 60 meters above the ground. Okay, we're taking the ground level to be 0. Okay, so we're measuring everything from ground level. And so since we're throwing this ball off the top of the 60-meter tall building, our initial displacement is 60 meters above the ground. Okay, now we want to know what's the position at t equals 1. Start there. And what the fundamental theorem of calculus tells us is that d of 1, right, the position at 1, minus the position at 0, whoops, is equal to the integral from 0 to 1 of the d prime, which is the velocity of t dt. Okay? And so if we want to find the position at t equals 1, so d1, then if we just add d0 to both sides, we get d at t equals 0 plus the integral from 0 to 1 of the velocity d prime of t dt. Okay, so we can find the position at t equals 1 just by taking the initial position and then adding the integral between 0 to 1. And the integral is just the area here. It's this area. Well, I don't know if I want to shade it. Otherwise it might get too messy. So we got to figure out what's that area. Well, one of the there's a number of different techniques you could do to find area, but in this case we can just look at this grid on this graph here, and you can see that the dimensions of any one little grid rectangle on this graph is 10 by 1. So that's telling us that each grid rectangle represents 10 by 1 meters, right? Represents 10 meters, okay, because it's basically 10 meters per second by 1 second gives you 10 meters, right? The seconds cancel. So let's just use that because that's easy enough to do. So if I look at this, so this represents 10 and this looks like it's half of 10. Okay, so in order to get the position at t equals 1, we're going to take the initial height, 60 meters, and we're going to add 15 meters to that. So we get 75 meters, right? Because we tossed the ball up, and so it has some initial velocity going up, but then gravity's pulling down on it and slowing it down. So but it's still traveling upward until gravity can take over and start pulling it completely down. So so anyway, the position at t equals 1 is 75 meters. So let's pull that plot or put that in the table. Now we could also plot this too. We're supposed to sketch a graph as well. So we're starting out here at 60 meters, and then at t equals 1 we're at 75. So I'll just go ahead and plot those points. Okay, I'm going to scroll down a little bit so I can have some more room to write here. But we won't be able to say the problem statement, but that's okay. You know what it is now, right? Okay, let's find the d at 2. Okay, so again, I could rewrite it this way. I don't want to rewrite this every time. But essentially, the distance, or the position at 2 is just going to be whatever the position at 1 was. And we can just add the integral from 1 to 2 of the velocity. Okay. And so our position at 1 was 75. And now the integral from 1 to 2 is this area. It looks like it's just 5 meters. So we're going to add 5 meters. And we have 80 meters total. So we can fill in the table and we can plot that point at t equals 2. And it's just a matter of just continuing in this manner. So at t equals 3, we're going to take the position at t equals 2 and add the change that happens from 2 to 3 dt, right? So from 2 to 3, okay, it looks like 80 meters is as far as we're going to go. Here at 2, the velocity was 0. So this is the point, this is sort of our critical point of the displacement function, right? This is where the displacement goes from being positive, or sorry, goes from being increasing, right? The displacement stops increasing and starts decreasing. So our maximum occurs here. This is our our maximum, or we call it our local maximum, but it's also the maximum of the function. Okay, so down here from 2 to 3, we have a negative area, right? It's the same area, but it's a -5, right? This area from 2 to 3. So to get the position at t equals 3, we're going to take the position at 2, 80, whoops, 80, and we're going to now subtract 5 because we have negative area. All right, so 75 meters. All right, so we're back down to 75 meters at t equals 3. All right, so we'll just keep going. At 4, we're going to take the position at 3, and we're going to add the integral from 3 to 4 of the velocity. Okay, and so we had 75, and now the area here between 3 and 4 looks like it's going to be 15, but in the negative direction, right? So we're losing 15 meters of displacement from the ground. So we're going to end up with 60 meters. So we're back down to the height of the building, right? We're assuming we're kind of throwing this off the edge of the building. So it's going to be like reaching out over the edge of the building. And so even though it's now back at the height of the building, it's not going to hit the building. We're going to assume it's going to keep going and all the way to the ground. All right, we got a couple more here to do. Let's see, do I have room? D equals 5. I'm going to take the position at 4 and add the integral from 4 to 5, d prime of t dt. So I take 60, and then I have to figure out what is the integral between 4 and 5. So it looks like we have 10, 20, 25. So in the negative direction. So we have an area of negative 25. Whoops, 25. 25. So 60 minus 25 gives us 35. Oops, I've not got to go ahead and fill in the rest of this table here. I'm plotting the points and I forget to fill in the table. All right, so so we can plot that point at t equals 5, and we're at 35 meters. So that looks like we're about here. Okay, one more. Let's see if I can make some room here. So I can show one more calculation. I guess I'll have to write it down here. D at 6. The displacement at 6 is the displacement at 5 plus the integral from 5 to 6 of the velocity. Okay, so we're going to take 35. And let's figure out what that integral is. We got 10, 20, 30, 35. So lo and behold, we just hit the ground, right? 35 minus 35 is 0. Okay, now plot that. So, we're getting so close to just being able to, we're getting all kinds of information now. Let's see, this is 0. About the original function from the rate of change, right? We started with just velocity, just looking at the velocity, and then of course, looking at the behavior of the velocity. It looks like in this case we got constant acceleration in the negative direction, and now we're getting really close to being able to find what the function, the original function itself is, because I can connect these dots and it looks like we have a nice curve, right? Kind of what you'd expect for a ball, right? A nice parabolic curve. So, the next logical question is, can we find the function that models this behavior given its derivative, given the derivative? Okay, so, all right, so there's one example. The next, there's only really 2 examples in this lecture. The next one involves marginal cost. Okay, so in business, oftentimes you're interested in, what's the cost to produce one more item at any given time, and it might vary depending on how many items you make. The more you make, perhaps the cost goes down. You can buy things in bulk, or you can, you have economies of scale. And so that marginal cost is not necessarily a linear function. It varies depending on how many how many items you produce, right? So so these next examples involve the concept of marginal cost. And marginal cost is essentially the rate of change of the cost function with respect to quantity. How much does it cost to produce one more at any given point in the production quantity? Okay, so so that's marginal cost, and then there's also the concept of fixed cost, because there are some overhead costs, like say rent or employee benefits, or I don't know, utilities could potentially, you gotta keep the lights on whether or not you're making anything, right? Gotta heat the building space. You had to pay for the garbage collection, whatever. You've got certain fixed costs associated with running a business. And so we're going to look at this, basically applying this concept of the fundamental theorem of calculus to some problems involving marginal cost. Okay, so if we call C prime of Q, if that's the marginal cost, and C of 0, right, is your fixed cost, right? So it's just a cost associated with making nothing, right? Just to keep the lights on. Then the cost to increase production from A units to B units, all right, is the difference in cost, the cost to produce B minus the cost to produce A. And using the fundamental theorem of calculus, we can take the integral of the marginal cost, okay? So, and then the total variable cost is that integral. The total variable cost to produce B units is the integral from 0 to B of that marginal cost. And then if we want to know the total cost, then we need to add the fixed cost and the variable cost together. Okay, so our fixed costs were the C0, right? C at T, or at when producing no quantity 0, if it's the cost of producing nothing plus how much it costs to produce B units, the total variable cost of producing B units. Okay, I don't know, this looks like a lot of equations, and so things usually make more sense once you actually look at an example. So let's look at an example. Hopefully this will all make more sense. All right, so in example 2, we're given a marginal cost curve, right? Now we're given it graphically. We aren't given any kind of data or a function itself. Here we're just given a graph. And it says that the fixed costs are $1,000, and we're asked to estimate what is the total cost of producing 250 units. Okay, so here's 250 units right here. So now we know that the total cost, right, the total cost, just as I said in that previous box, the total cost of producing B units, which in this case B is 250 units. So the total cost of producing 250 units is going to be the fixed cost, which in this case is $1,000, plus the integral from 0 to 250 of the marginal cost curve, dq. Okay, so that's what we've got to do. We got to figure out the integral of the marginal cost curve, which is just going to be the area under this curve. So let's take a look at this. The scale on this, it looks like, if I look over here, it looks like every rectangle is 2 by 50, right? So it's $2 per item times 50 items. So that's represents $100. Okay, so when we integrate this curve, each grid square represents $100. And so now we have to estimate how many grid squares there are. Okay, so some of them are pretty easy to count. 1, 2, 3, 4. We'll count this one. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We'll count this one. 16. And then from there, it's kind of like, well, 17, 18. We'll count this as 1, 19. And then we've got this one and this one and this one together might make 1. Okay, so I estimated that there are about 20 grid squares underneath that curve. And then if each grid square represents $100, then we have 20 times $100. Oops, not 1,000. Okay. And that's $2,000. Okay, and that is our integral. That's our integral from 0 to 250. 250. Guess I left out a 0 here. 250 of the marginal cost curve. Oops, Q dq. Okay, so that's our integral, and then we can just add it up. The total cost then is equal to the sum of the fixed cost, which is $1,000, plus the $2,000 variable cost, total variable cost. So we get a total of $3,000 is how much it costs to produce 250 items. So that's fixed cost and variable costs. All right, so that is it. Hey, it's kind of nice to have these shorter lectures, right? There's practice problems. Oh, where are the practice problems? There are practice problems. Should be in your notes. I don't know where they are. That's strange. I didn't put them in here. So I'll let you work on those, and then you can work on the exit ticket, and we'll see you next time.